We're going to discover some of the properties of the orthocenter of the triangle. For example, suppose we take the orthocenter and we take the reflections with respect to each of the three sides. So for example, taking this side, and we reflect the orthocenter with respect to this side, this point goes here, then it turns out that this reflection lies on the circumcircle of the triangle. And similarly, all the other reflections, this reflection and this reflection, so this point and this point, also lie on the circumcircle. And now we're going to prove this. We're going to take this altitude and we're going to intersect it with the circumcircle at this point. And then we're going to prove that this length equals this length. And it would follow that this is actually the reflection of the orthocenter with respect to this side of the triangle. Now consider this angle here and this angle here. Well, they're equal because this quadrilateral is cyclic. And it's cyclic because we have a right angle here and a right angle here. Furthermore, consider this quadrilateral here, which is cyclic because of this circumcircle. Well, this angle equals this angle. They both point towards this side, or this arc of the circle. And so, this angle equals this angle equals this angle. And now, in this triangle, we have an angle bisector and an altitude at the same time, which means that this triangle is isosceles. Or, in other words, you can consider this triangle, and they are congruent because they share a common side and they have the same angles. And so, this length equals this length, and therefore this is the reflection of this point with respect to this line. And similarly, we have that this equals this, and this equals this. Now we're going to consider another reflection, but this time not with respect to the side, but with respect to its midpoint. For example, this midpoint of the same side. I'm going to reflect this point with respect to this point here, and now I'm going to prove that this point also lies on the circumcircle of the triangle. And similarly, the reflections with respect to the midpoints of the other two sides, like this and like this, also lie on the circumcircle of the triangle. Now see what we've got here. We have a segment and another segment that share a midpoint, such that the reflection of this point with respect to this point is this one, and of this point with respect to this one is this one. And therefore, by the properties of the parallelograms, this is a parallelogram. And because it's a parallelogram, we know that this angle here equals this angle here. The opposite angles in a parallelogram are always equal. But this angle here also equals this angle. And now take a look at this quadrilateral. It is cyclic because we have a 90 degrees here, 90 degrees here angle. Their sum is 180. And therefore, the sum of this angle and this angle is 180. But remember that this angle equals this angle. And so the sum of this angle and this angle is 180 degrees. Here I've marked the angle gamma, 180 minus gamma, 180 minus gamma, 180 minus gamma. And therefore, this quadrilateral is cyclic because the sum of this angle and this angle is 180 degrees. And this circle is actually the circumcircle of this triangle. Notice one more thing here. In this parallelogram, the pairs of opposite sides are parallel. We have that this side is parallel to this side, but this is perpendicular to this side, and therefore its parallel, this one, is also perpendicular to this side. Similarly, we have a right angle here. So we got that this here is actually a diameter of the circle, because a diameter makes an angle 90 degrees with a random point on the circle. So the center of the circle is the midpoint of this diameter, so I'm putting it here. And we know that because this is a center, this equals this as radii in the circle. And so this is an isosceles triangle in which this is a median, and so it is also an altitude. Or we know that this point basically lies on the perpendicular bisector of any chord in the circle, for example this one. What's interesting here is that we have a mid-segment in this triangle. Consider this triangle here. This is a midpoint, and this is a midpoint. So this is midpoint, and this is a midpoint. And so this is a mid-segment in the triangle. And this is not surprising since this is actually parallel to this, obviously, because this is a right angle and this is a right angle. The more surprising fact is that this length is half of this length. And so if this is x, this is 2 times x. And of course, we can make the same arguments for the other two sides of the triangle. For example, if I take the midpoint here of this side and I connect it with the center of the circle, then this would be 90 degrees. And then, for example, if I reflect the orthocenter with respect to this midpoint, the reflection will go here, it will lie on the circumcircle, and then this would be a diameter, just like we had a diameter here, we would have a diameter here, and therefore this length would be half of this length. And so if this is y, then this here is 2 times y. The optional problem is, take a triangle and take its circumcircle. and then take an altitude here and here. Then take this triangle, this small triangle, and draw its circumcircle, and let it intersect this circumcircle here at this point. Then this is the orthocenter of the triangle, and this point is the midpoint of this side. And you should prove that this point, and this point lie on a straight line. And here is the solution. First thing to notice is that this point here, the orthocenter, actually lies on this circle, on the circumcircle of this triangle, because this quadrilateral here is cyclic. After all, we have that this angle is 90 and this angle is 90, so their sum is 180. Now I'm going to reflect the orthocenter with respect to this midpoint, and as we know, the reflection lies on the circumcircle of the triangle. And now I know that if we take this segment here, this would be the diameter of the circle. Indeed, after all, this is a parallelogram because of the two midpoints here and here, and so this line parallel to this line, but this line is perpendicular to this line, and so this line and this line make a right angle here, and similarly, we have a right angle here. And because of this right angle, then this segment must be the diameter. And so the center of the circle lies somewhere here in the middle of this segment. Now, what is the angle between this point, and this point? So this angle here, but not with respect to this point or this point, but with respect to this point down there. So this angle. Well, it's 90 degrees because this is the diameter of the circle. So now if we prove that this angle here with respect to this point is 90 degrees, it would follow that this point, and this point lie on the same line. And that would be the end of the solution. Let's see why this angle here is 90 degrees with respect to this point. So why this angle is 90 degrees? Well, consider this circle. This is a diameter in this circle because we have a 90 degrees here and a 90 degrees here. And so the angle here is also 90 degrees. We have a cyclic pentagon here such that this angle equals this angle equals this angle equals 90 degrees. And so because we have a 90 degrees here with respect to this point and 90 degrees here with respect to this point, then these three must lie on a straight line, and so problem is solved.